we've reached the last component in the refrigeration cycle components. And that's where the action is. If you have a refrigerator or an air conditioner, the evaporator is what's absorbing the heat from that cold space. And that's your objective when you have either an air conditioner or a refrigerator. So let's have a look at what you're going to be analyzing for the evaporator part. Okay, so this is going to finish off our fourth component, and then in the next video, we're going to look at maybe putting it all together, and I'm going to try to give you some ideas of typically what's asked out in the world and in many homework problems, what's typically asked of you to do in your full cycle analysis. So let's remind ourselves, what do we got? Here's our four components, and we're interested in analyzing the evaporator part. It's just a plain old heat exchanger. Open system, steady state, steady flow, one inlet, one outlet. Refrigerant, cold refrigerants coming in as a saturated mixture at state 4, and it's leaving as a also cold saturated vapor at state 1, going back to the compressor. So what does this look like in the TS diagram? So we're trying to put it all together. Remember that we've come out of the expansion valve, a throttling valve, where the pressure has dropped dramatically, but the enthalpy stayed the same to a lower pressure. And so you're going to be able to, if you do a little numerical work with any of the refrigerants, you're going to see that at a given pressure, P4 or P1, you're going to see that temperature really becomes very, very cold for these refrigerants we're working with. Okay, so we're coming into the evaporator, which is just a plain old heat exchanger, at some saturated mixture, some quality X4, and we're absorbing heat. So we're evaporating the refrigerant, and it's going to become a saturated vapor to go back into the compressor. So it's a pretty simple looking process, a straight line, constant pressure, constant temperature process. And I hope that it's a reprise of, let's see, your chapter 3, where you've gotten good at evaluating properties of substances that are under the vapor dome. You've gotten good at that. You've gotten good at analyzing open systems in chapter 4, and you're going to be putting all that together here for our refrigeration cycle. So what does the evaporator look like? Well, I've dug out what a refrigerator evaporator coil looks like. Here's sort of a rectangular unit, but you get the idea. There's going to be basically it's going to be a finned coil or tube. Probably will be aluminum fins to maximize the heat transfer between the refrigerant contained within the heat exchanger tube all the way to the air in your freezer section. So freezer air is blowing across the evaporator coil, and that's what's keeping your ice cream and other substances in your refrigerator either frozen or cool. So refrigerator evaporator coil, pretty compact rectangular type design. For a whole house air conditioner, this is what an air conditioner evaporator coil looks like. It looks a little bit like a trapezoid. And what's going on here is that, well, you see these copper tubes. We've got an inlet and an outlet of the refrigerant. Now let's see. What's coming out is a saturated vapor, and what's going in is a saturated mixture. So I'm going to sort of guess that what's going in is through this copper. Okay, a mixture of vapor and liquid refrigerant going in, and what's coming out is going to be saturated vapor. So it would, my intuition is it would be rising to the top, and I would think that this is going to be the outlet that's going into the compressor. So that would be the refrigerant side. Well, how are we cooling? How are we keeping you nice and comfortable inside your house? Well, what we're doing is we're returning warm air from your house that's kind of heated up, and it's coming in a duct. It's coming in a duct, and it's flowing on the inside of this sort of rectangular box. And so therefore it's flowing across these finned cooling coils. And so what's coming out of this sort of duct type arrangement is very cool supply air that's going back to your room in your house. And that's going to make you nice and comfortable. That type of thing as you stand underneath the air registers in your apartment or townhouse or home or wherever you live that's using a whole house air conditioner. So anyway, this is what the air conditioner evaporator coil looks like. And here's another picture of how it would sit in the big boxy thing that you may hear whirring around when the air conditioner is running. So you know you're not listening to the compressor. The compressor is going to be outside. Probably what you're hearing is the blower fan that's pulling the warm air from your rooms and blowing it across this evaporator coil. Here it is. Okay. And so that's how I got so you can see in cross section how this piece of equipment is kind of like a hat or a trapezoid. So you can see how the air is flowing in through the inside of these coils, blowing across the cooling coils where the cold refrigerant is, and then supply air going back to your room, back to inside your house. So you get the idea of how it all fits together. And what you're going to be hearing in that big boxy thing is the blower that's blowing the air around inside your house. How about the automotive air conditioning system? Well, this is going to be a little rectangular evaporator where your cabin air is being blown across this evaporator somewhere underneath your dashboard. Uh, I'm going to guess on the passenger side or maybe in the middle of the vehicle. But you get the idea that cabin air is being blown across this evaporator, what's keeping you nice and cool inside the cabin of your car. Okay, so this is a pretty good overall view sketch of all the components in the air conditioning system for your car. And I see here, so for example, it says orifice/expansion tube. And so that would be an example of, I think, what we call the capillary tube for smaller size air conditioning units. Let's talk a little bit about a heat pump evaporator. Would the heat pump evaporator be? Well, interestingly, wow, this thing looks familiar. You've seen this picture and you recognize this as the unit that's sitting outside of your house. And you say, wait a minute, in a couple of videos before, you called this the condenser. And I did. So in the summertime, this unit here is serving as the condenser where you're trying to transfer heat from your house, cooler, out to the surroundings, hotter. In the wintertime, you're wanting to get heat transfer from the outside where it's cold, and you want to transfer heat to the inside where it's warm. And so strangely, the flow actually reverses, and this unit here serves as the evaporator section for a heat pump. And there are some great videos. If you go to the This Old House channel on YouTube, the This Old House guy, Steve, he has some great videos talking about how a heat pump works compared to an air conditioning system. I find it to be very interesting and very educational if you go to This Old House channel and look up heat pump. So anyway, the idea here is that in winter operation, this unit outside your house is serving as the evaporator. Okay, now back to your problem solving. What does your sketch need to look like? So your sketch is going to look like a basic heat exchanger, one inlet, one outlet heat exchanger, steady state, steady flow, open system, coming in at state 4, leaving at state 1. And let's see, what have I labeled on my sketch? I have labeled, do you see this heat exchanger lifting a weight, shaft rotating at a known torque? No. So W dot out is 0 for this sketch. How about Q dot in? Yes, it's positive because heat is flowing from the surroundings into the refrigerant. So Q dot in is greater than 0. Got it. Okay. P4 equals P1. So this is a plain old heat exchanger, very low pressure drop. So we're going to say for our mathematical model, P4 equals P1. Going to remind ourselves that little q for an open system is Q dot over M dot. Remember, the M dots are the same inlet and outlet for one inlet, one outlet. So little q is Q dot over M dot. So we can write the first law. In the absence of kinetic energy changes, certainly there's no potential energy changes. So we've got Q in, that's going to be a positive number, minus W out. We strike that out, no work involved, equals H1 minus H4. So you see that right in your book, right? And so it's a simple matter to calculate the heat added in the evaporator, H1 minus H4. So what's that going to look like on the TS diagram? So very simple. Here's our process 4 to 1. The first law, I think you've got that covered. Okay. The heat added, Q in is, let's see, H1. How did you get, you've already got H1 because you've already analyzed the compressor. H4, well, you had H4 because you've already analyzed the expansion valve and you've got H3, right? So this first law becomes very easy. And so on this one, not only is it valuable to look at the TS diagram to see how simple looking the process is, it's constant pressure, constant temperature, heat addition, we're evaporating, right? So it's like, how can there be heat transfer when it's constant pressure, constant temperature? Well, easy. What we're doing is we're changing the phase. We're changing the phase of the refrigerant from saturated mixture to saturated vapor. That's how we add heat at constant temperature, okay? And the extra credit part is, so a very common quiz and test problem is, can you determine a value for X4? What's the quality at state 4? And I would claim that it's really very easy to do because, look, you've already got, so it's a ratio. Quality is a ratio, isn't it? It's this distance that I'm circling here divided by this total distance here in terms of enthalpy, because you have the enthalpy. And so the ratio is going to be, so X4 is simply going to be H4 minus HF. So you see, that's that distance, divided by the quantity, Hg minus HF. This distance right here, G minus F. And so that's the way you determine X4, and that can be a lifesaver when you have a quiz or a test and that question is asked. Very commonly asked question on a quiz and a test. So we've got our evaporator analysis. So remember, the evaporator is constant temperature, constant pressure. It's a heat exchanger. It absorbs heat from the cold space. Okay. The inlet to the evaporator is a saturated two-phase mixture, as you saw on the TS diagram. And the outlet is traditionally a saturated vapor at that same temperature. Sometimes it can contain a little superheat at a little higher temperature, but rarely. And so you may have a homework problem where the inlet to the compressor is slightly superheated, but not by very much. So traditionally, saturated vapor at the evaporator outlet. That covers all 4 components. Sounds familiar, didn't it? So all 4 of those components were kind of rehashes of Chapter 4, steady state, steady flow, open system, one inlet, one outlet, coupled with Chapter 3, where you're looking up properties of phase change substances. So I hope that's taken some of the mystique out of analyzing refrigeration cycle processes. And what's coming up is I'm going to try to give you an idea of typical things that are asked both in homework problems, but also out in the real world of when you're faced with analyzing an air conditioning system, a refrigeration system, a heat pump. What kind of things are typically asked and what kind of things are typically given to you as part of that analysis? So I hope that helps you feel a little more comfortable about analyzing the cycles, the refrigeration and heat pump cycles in Chapter 10.